In this last video cast on gases, we'll take a look at some of the results of something called the kinetic molecular theory and the four postulates that that brings about, and then some applications of that to find molecular speed and to find the rate at which gases diffuse and effuse. We'll start with sample exercise 10.13, but before we do that, there's just a couple of quick notes to give you to help identify and actually understand what the kinetic molecular theory says. Well, the kinetic molecular theory says that gases are all made of very small particles, and they're in constant random motion, and they're colliding with each other, causing pressure, obviously. It also says that the particle volume is extremely small compared to the whole volume that the actual gas takes up. And so we actually ignore, in an ideal gas, the size of the small gas particles. We also ignore the attractive or repulsive forces of an ideal gas. We assume that since the particles are so far apart, that they really don't have a lot of attractive and repulsive forces. And we'll find out in real gases this isn't exactly true. And we also know, or we also assume, that the kinetic energy of the gas, in other words, the energy of motion of the gas particles, is directly proportional. That's what this little sign here means, is proportional to temperature. In other words, if the temperature goes up, the kinetic energy goes up. Or if the kinetic energy goes down, the temperature goes down. And we assume that the temperature or the kinetic energy does not change without a temperature change. One good contrast or contrary example of this is if you have two gases, like for instance helium and krypton, although they are very different in molecular size, since we ignore these sizes, if they're at the same temperature, we say they have the same kinetic energies. Well, using kinetic energy, you can actually calculate how fast various gas molecules move. And if you take a look in your textbook on page 423 of Brown-Lemay-Bernstein's 10th edition, the average kinetic energy of any collection of gas molecules has a specific value at a given temperature. Well, the mass of the particles in the lighter gas, of a lighter gas, is smaller than the heavier gas. Consequently, the particles of the lighter gas must have a higher velocity. They don't actually say the word velocity, they'll use a special kind of speed with gas molecules. And since gas molecules are smashing off of each other and changing direction all the time, we look at the average speed that these gas molecules are called, and the special average they use is called RMS speed, RMS, which stands for root mean square. And take a look around this page in your textbook and it'll define for you just a little bit more about what RMS actually means. It's close to the actual average, but it's just a tiny bit different. Anyway, the equation to find out this speed is equal to the square root of 3RT divided by the molecular mass of the gas. This little U symbol right here sometimes has an RMS below it, which means root mean square velocity or root mean square speed. We'll just talk about it as speed and kind of being the average. Sometimes you see a line over the top of it too, meaning average speed. Notice it's inversely proportional to the molar mass. In other words, smaller things move faster, heavier things move slower. And we'll do a sample problem with that in just a second. A second consequence of the kinetic molecular theory is that molecular speeds and mass allow you to take a look at a couple of different phenomena called effusion and diffusion. Effusion is the escape of gas molecules through a tiny hole into an evacuated space. Great picture of this in your textbook on page 424. Right here, I'll show it to you so you don't have to haul it out if you don't want. But you can see right here, there's a whole bunch of gas particles in this, and some of them are going through this little tiny hole right here. And if you zoom in just a little bit, you can see that some of the gas particles move into this other space. How fast that happens is a result of molecular speed. Well, the other one is called diffusion that I related to. And diffusion is when one substance is spread out throughout a space or throughout a second substance. Anyway, the equation that we can use to calculate that is that the rate of one substance compared to the rate of another is inversely proportional to the square root of their molecular masses. This is called Graham's law. And we'll use that as well when we do some sample problems today. Let's go back here to sample exercise 10.13, and I'll zoom in just a little bit on this. And it says in sample exercise 10.13, a sample of O2 gas initially at STP is compressed to a smaller volume at a constant temperature. What effect does the change have on the average kinetic energy of the O2 molecules? Well, we compressed it to a smaller volume. We did not change the temperature. And we did not change the number of moles of gas at all. And since we didn't change the temperature, temperature is directly proportional to kinetic energy. And so the average kinetic energy is unchanged. By changing in volume, it only, remember that average kinetic energy is only affected by a change in temperature. And since there is no temperature change here, therefore, there is no change in the kinetic energy. Let's look at the second one. It says the average speed of the O2 molecules. Because the average kinetic energy doesn't change, the average speed remains constant as well. So speed remains constant. The average speed, remember, it's always average speed. Obviously, there'll be molecules that are going slower and there'll be molecules that are going faster, but we look at the average of all of them. Letter C. I'm at D there. Let's look at C. The total number of collisions of O2 molecules with the container walls per unit time. Well, the number of collisions will increase because the molecules are moving at the same rate, but in a smaller space. So the molecules are at the same speed, but smaller space. So what does that mean? Well, you squash the molecules into a smaller space, they're obviously going to collide a little bit more. Okay, and then letter D, the number of collisions of O2 molecules with a unit area of container wall per time. Well, the number of collisions increases because the total number of collisions with the wall increases and the area of the wall decreases as well. Well, let's take a look at a couple other sample exercises. 10.14. This one takes into account the RMS, root mean square speed of a nitrogen molecule at 25 degrees Celsius. And it asks us to calculate this. You have to be kind of careful with the equation that I showed you earlier. The equation that I showed you earlier was that RMS speed is equal to the square root of 3RT divided by molar mass. Remember that R is usually given to us in liters. And the R that we use in this equation is actually the 8.31, and the units on this are gonna be a little strange for you, because the derived units, the units I gave you before, were kilopascals times liters per mole times Kelvin. Well, you can derive this kilopascals portion right here into a little bit different set of units. And the units actually follow that you can take the kilopascal and the liter, combine those two together and get something called a unit of energy, the joule. And the joule is actually a kilogram times meter squared per second squared. And on page number 424, if you're interested, you can see the derivation of where the units for this actually come. So ignore those units for now, and just know that the units are going to be 8.31. The ones we're going to use in here are kilogram times meter squared per second squared times mole Kelvin. Okay, that's what the units on the R, or the universal gas constant, that we're going to use are. Notice the consequence here. The mass is given in kilograms. That means that our molar mass down here is also going to have to be in kilograms, because we want the masses to cancel with one another and end up taking the square root of meters squared over seconds squared right here to get our units of meters per second. Temperature, of course, should also be in Kelvin. You can see that this is the Kelvin temperature right here. All right, so it's nitrogen gas at 25 degrees Celsius. Let's plug and chug some numbers here. 3 is in the equation already. R is going to be the 8.31, and I'll use these units, kilograms times meters squared per second squared times mole times Kelvin. And the temperature here is going to be 298 Kelvin. Notice our Kelvins will cancel with our Kelvins here. This is a 2. I don't know if that showed up quite so well. Okay. And then we divide that by the molar mass. The molar mass, remember, if we add it up on the periodic table, is 14 plus 14 or 28 for nitrogen. But remember, that's in grams per mole. What does it have to be in here? Yes, kilograms. So make sure that you take and convert your 28 grams per mole and put it times 10 to the negative third. That's supposed to be an x there for times 10 to the negative third. And that would be in kilograms per mole. Now your moles will cancel with your moles, your kilograms with your kilograms, and you're left with meters squared over seconds squared. You can take the square root of that monster, multiply those guys together, and you end up with a root mean square velocity of 5.15 times 10 to the negative 2 meters per second. That is our root mean square velocity of nitrogen gas molecules at 25 degrees Celsius. Let's look at this sample exercise, 10.15. An unknown gas composed of a homonuclear diatomic molecules diffuses at a rate that is only 0.355 times that of O2 at the same temperature. Calculate the molar mass of the unknown and identify it. Well, remember the equation that the rate of one gas compared to the rate of the other gas is equal to the inverse of the molecular mass of the two gases? Well, that's where this equation comes in. Remember, this is called Graham's law. And since we know that one rate is 0.355 times that of oxygen, what we can say is that the rate of the unknown gas, we'll call it X, compared to the rate of O2 is equal to 0.355. And this is equal to the inverse of the molecular masses. So since O2 is on the bottom here, we'll put 32 grams per mole on the top, because that's the second molecular mass, and that's the second rate right here. And this is the molecular mass of our unknown gas. Solving for molecular mass down here, squaring both sides, and then taking molecular mass, solving for molecular mass right here, we end up with molecular mass is equal to, I'm not sure that I have an intermediate here, but 32 grams per mole divided by 0.126. Yes, I do have that squared. 32 divided by 1.126 is 254 grams per mole. Well, there was a clue up here. It said homonuclear diatomic molecule. Okay? Homonuclear means similar all throughout. Diatomic means that there's two of the elements stuck together and that it's a molecule. So if you know it's diatomic, divide it by 2 and you have the molar mass of one of them. I think it turns out to be about 126, and if you look on the periodic table, that is iodine. And so our diatomic molecules happen to be I2. Well, we talked about the situation where we made some assumptions in the gas laws. We assumed that gas particles were in constant random motion. We assumed that the particle volume was small. We ignored these attractive and repulsive forces, and we assumed that the kinetic energy was directly related to temperature. But what about in the real world, where the particle volume maybe can't be ignored, or where the attractive repulsive forces can't really be ignored? Well, we're lucky. A gentleman named van der Waal came up with an equation to take into account these small differences that we sometimes ignore and might not rightfully ignore. Well, his equation turns out to be the ideal gas equation, but corrected for these assumptions. PV equals nRT divided by volume minus NB. These little numbers right here correct for the volume that the molecules actually take up. Notice they're subtracted from this volume because the volumes in the molecules actually do take up just a tiny little bit of space. Mostly we can ignore them though. Minus n squared times A divided by V squared. This term right here corrects for the molecular attraction in the molecules. Now, A and B, you'll say, hey, what are those? I've never seen those before. Well, if you look in Brownell-Mayburson in chapter 10, well, this is edition 10 as well, page 429, these are the van der Waals constant for various gas molecules. And the amount of attraction, and of course the volume that the gas molecules actually take up, differ depending on what they are. If you look at the bottom of page 429, I'm not sure I can fit it in here. Here it is right here, crooked. But here's the table of van der Waals constants A and B for various gases. And you'll see that as the gases get larger, like CCl4 right here, really big, obviously you have to take a lot more into account for the attractiveness and the voluminous or volume size of those gas molecules as well.